curriculum. So first of all, I would like to thanks Mariana for accepting our invitation for our seminar. So as I said, here we are with Dr. Mariana Cécere. She's an adjunct researcher and professor at the Instituto de Astronomía, Teórica y Experimental at Córdoba, Argentina. Her main research is based on the MHD, magnetohydrodynamic numerical simulation of solar physics phenomena at the coronal level, namely coronal loops, super-K downflows, Morton waves, filaments, and coronal mass ejections. Right now, she's in Graz, in Austria, and today she's going to talk about energy release in solar flares, insights from MHD simulations. So, Mariana, you have the floor.
Okay, thank you, Fabian, for the invitation. So as you said, the idea of this talk is try to show the work that we performed there in Córdoba. In this case, our expertise is to do these MHD simulations in order to understand the physical mechanism responsible to produce some energy release in phenomena related with the solar flares. First of all, I want to present our group in Córdoba. We live here in the middle of Argentina. In our group, we are 4 researchers, Andrea Costa, Ernesto Zubrigen, and Federico Stasicin. And we will have these 2 new students, Rubén Sandes and Tadeo Makarov. As Fabian mentioned, we work in the Astronomical Observatory of Córdoba, but also we are researchers in the Institute of Theoretical and Experimental Astronomy. And we try to understand what happened at coronal level, and we study different solar phenomena through the MHD simulations. As Fabian mentioned, we try to understand why the Morton waves occurs after a CME or a flare. Also, we try to emulate we try to emulate flares in order to see how this energy release is able to produce, for example, Morton waves or not. Also, with MHD simulations, we propose a new model in order to understand which are these particular behavior of these dark regions that are descending toward the sun, these super-K downflows. Also, we try to understand with numerical simulations why these coronal loops oscillate in flaring regions, but also we try to understand which are the physical mechanisms responsible to produce the damping behavior in the oscillation in prominences. And we try to understand why a coronal mass ejection could be deflected or maybe could be failed in the ejection. So in this talk, I will talk only about these 2 topics, the coronal loops and CMEs, and I will start with the coronal mass ejection. I don't know if anybody knows what is this, a coronal mass ejection. We can see here, this is a prominence of filament. This chromospheric material is ejected to the interplanetary medium when instabilities occurs. So first, we think that we have this kind of magnetic structure, we call it magnetic flux rope, that first is sustained this filament, this chromospheric material, but then occurs several instabilities and the ejection occurs. When we see the same event, but with a coronagraph, here is the sun occulted by the coronagraph here, we can see how this material is ejected, and we can see here how this plasma is propagating toward the interplanetary medium, and this is very important to the space weather because, as you can see here, this plasma interacts not only with the planets, in this case the dot points, but also interact with the instrument, in this case the squares. And this plasma, the electron and protons, can damage the instrument. So it's very important to predict, for example, if a CME will occur. It's important to know the direction, but also it's very important to know if a CME will fail. So in 2020 or 2019, we start to try to understand why the CME deflection occurs. Here I show you a CME propagating radially, but sometimes happen that the CME, for example, if you see here, we have the source of the CME, but propagates toward the equator. The propagation is not radial, and why this happens? And this happened because the topology of the magnetic field lines in the sun is very complex. We can see here how complex it is. We have several structures, pseudo-streamer, streamer, coronal holes. We have a combination of closed and open magnetic field lines. And when we try to understand why a CME could be deflected, we have to think in the forces. And if you pay attention here, for example, we can see here that the polarity or the direction of the magnetic field lines are in opposite directions, and in the middle, the magnetic field lines is 0. Here, all happen the same in this more complex structure, the pseudo-streamer. So these regions, the magnetic field lines are very, very low. And if you think in the forces, here we can see the Lorentz force, the gradient of the pressure, and also the gravity. And the Lorentz laws, we have the tension and the pressure. And if we have a gradient in the magnetic energy, we will have a force. And these regions, in that sense, act like as attractor for the CMEs, because the CME feel this force in order to this region of low magnetic energy. So this could be a good reason for the deflection of a CME. But what happened, for example, for pseudo-streamer and Helmet streamer? But the coronal holes, what happened? These magnetic structure are composed by only open magnetic field lines, and we don't have this kind of forces here. So it's not so clear what if a coronal hole has an influence on the deflection. But from the observational side, the people tell us that the CMEs, the coronal hole act as repulsors. Why? Because, for example, in this case, in this work from FLARES et al. 2006, they measure a lot of events. In this case, these regions are coronal holes. The coronal holes in UV, we can see here these dark regions that tell us that they are coronal holes. And when they measure the direction of the CME, in this case, is in this in the direction of this blue arrow, and correlate with this kind of force that they define in this way, which is proportional to the area of the coronal hole, inversely proportional to the distance from the source to the coronal holes. And then Gopaswamy in 2009, they also realized that also depends on the strength of the magnetic field of the coronal hole. Again, you can see in these images here that the force is and the red arrow, and the direction of the CME is the blue arrow, and is more or less correlate. So they tell us from the observations that the CME moves away from coronal hole. So in order to try to understand the physical mechanisms, we have to model a CME using the MHD equations, and we need to know the CME parts. So in what light, we know that we have a leading edge, this cavity and the core, the source of the CME. But when we saw it in a very low altitude, here we see that this is the cavity. Here we see the prominence, and we think that these helicoidal magnetic field lines first sustain this chromospheric material, and then when instabilities occur below, in this case magnetic reconnection, this detach the flux rope, and this produce the ejection and the CME. So in order to find the analytical formula for these magnetic field lines, we use the catastrophe model by Forbes in 1991, where he saw in this very simple scenario where we have two current wires in opposite direction in order to obtain a repulsive force. And in order to obtain this kind of magnetic field lines, he had this line dipole at depth D. And when you sum these three sources, you obtain this kind of a magnetic structure that is very similar that we see here in the observation in UV. The flux rope in this case is this current wire here. And we started with our simulations with this flux rope present in the initial condition of our simulations in a disequilibrium. So, but then in order to see how is the influence of, for example, in this case, the coronal hole, we add this another structure. And when we add these two magnetic field lines, the magnetic field line of the flux rope and the magnetic field line of the coronal hole, we obtain this null point region here, the region of very low magnetic energy. And if you pay attention, here we have the coronal hole, this is the flux rope, and the null point is located here. And this dashed line is the trajectory of the flux rope, the source of the CME. So you can see that with this simple scenario, we can understand why the flux rope is ejected away from the coronal hole. Because we have this gradient in the magnetic energy, so the flux rope feel a force toward this direction and produce the deflection. So using the flash code, we were able to see how the influence of the coronal holes produce this particular behavior. But as you know, when you see the sun, you obtain or you see anomalous behavior. And in this case, we wonder if a coronal hole can act like a repulsor. For example, in this event, these authors found that when they have this active region in the coronal hole, first the CME moves toward the coronal hole and then moves away. And in this work that we performed in 2020, we see more or less the same. We have here different active regions, and the CME moves in this case toward the coronal hole. But why? Which is the magnetic structure responsible to produce this anomalous behavior? Is due because we have an active region, or maybe the coronal hole could be able to produce an attraction for the CME? So in order to, again, to try to understand the influence of the coronal hole to the deflection of the CME, when we see again our previous work, we realize that the polarity between the flux drop and the coronal hole in this case is aligned, because if you see this is positive and positive, we call it in this case aligned case, sorry. But if the polarity of the flux drop now is anti-aligned, if you see here, this is minus and this is plus, now the null point is between the flux drop and the coronal hole. And this produces that the flux drop moves toward the coronal hole and then moves away from the coronal hole, as you can see in the through the this dashed line, this black dashed line. And in order to compare with an observation, we found this particular event that we have here the flux drop the coronal hole in an isolated way, because we don't have any another structure here near the flux drop. And when we measure the trajectory of the CME, this is this dot points here, and the solid line is the simulations, we found that in this case, the flux drop, the coronal hole attract the flux drop, and then the flux drop moves away from the coronal hole. So with this relative polarity, we can explain why change the trajectory of the CME. But as I mentioned before, it's very important to understand and to predict the trajectory of the CME, but also it's very important to predict when a CME will fail. So in that sense, again, the answer is in the magnetic structure, because as I mentioned before, we have these closed magnetic field lines, and these closed magnetic field lines, for example, in pseudo-streamer and Hermit streamer, produce this kind of magnetic cages. And this could be responsible to produce that the CME failed. Also, this structure has this region of low magnetic energy, so we expect that a deflection will occur, but maybe if this magnetic cage is very strong, the CME could fail. Let me see the time. Okay, so first, again, using the MHD simulations, we try to isolate the problem and see what happened, in this case, how the pseudo-streamer influence the deflection of the CME, but also how this pseudo-streamer can produce the failure of the CME. So again, we know from the observations that when you have a pseudo-streamer, in this case, this yellow line, the blue lines is the flux drop, and this red point is the region of low magnetic energy. You can see how the flux drop is moving toward this null point and then is ejected. And also in another event studied by Jan and collaborators, they see the same, that the flux drop moves toward the null point and then is ejected. So when we try to analyze the deflections with the MHD simulations, and again, we add the magnetic structure of the flux drop, and we added to magnetic structure of the pseudo-streamer. In this case, now we obtain two region of null point. The null point of the pseudo-streamer, but another region of low magnetic energy due to the presence of the flux drop. So when we analyze in this case the trajectory, we see that the flux drop first is the direction is toward its own null point, and then toward the second null point, the null point of the pseudo-streamer. But when we increase the strength of the pseudo-streamer, the magnetic field, the strength of the magnetic field, we see that in this case, the CME failed in the eruption. So if you can see the white lines, the topology is almost the same. Okay, we know that the background is twice stronger, but in order to try to quantify what is happening here, we measure the flux, the magnetic flux that this magnetic flux strobe must to cross, in the case that is ejected and in the case that failed. And we found that the violet one is the fail and the pink one is the successful eruption. We see that this magnetic cage flux is larger than the case that erupts. So in this way, we were able to quantify in a way how the magnetic cage influenced the flux of ejection. Then we try to do the same analysis now with helmet streamers, because again, you see that we have this magnetic cage here, and we see more or less the same effect. When the magnetic field is, in this case, 0.1 Gauss, the ejection occurs, but if we increase the strength of the magnetic cage, in this case, the CME failed in eruption, in this case, due to the erosion by magnetic reconnection, using again the same code, the flash code. But in this case, we measure the fluxes, the magnetic flux that this magnetic flux strobe must to cross, but also we measure the fluxes of the magnetic flux strobe, and we perform this ratio. And in these three cases that I show you here, if you see this is the helmet streamer, the flux strobe in the case one is in the middle, is very symmetric, but then we move the magnetic flux strobe toward the foot point of the helmet streamer. The white line represents the trajectory of the CME, so you can see that in these three cases, the ejection occurred. And when we measure this ratio in the evolution, in these three cases, case 1, 2, and 3, we see that this ratio is larger than 1.5. But when we increase now the strength of the helmet streamer, in this case, this is a background, we see that case 5 and 4 fail in eruption. And this ratio now is lower than 1.5. But the case 6, where the flux strobe is very, very near to the foot point of the helmet streamer, is still erupting. So the idea to do this ratio was try to find a kind of parameter in order to try to predict if a CME will erupt or not. And because if you see in the initial time, in the successful cases, this ratio is larger than 1.5, but every time happens the same. So if we know in the initial condition that this ratio is larger than 1.5, we can predict that the CME will be successful, but instead, if not, the CME will fail. Okay, this is the summary for this work that I present you for the CMEs. And now I will talk about the other topic about the quasi-periodic pulsations. And in this GIF, I show you this active region. We can see here the sunspot. And when a flare occurs, this happens when we see this brightness very, very strong. We can see now the loops, between the foot points. This arrow point out this foot point, but this arrow point out the top part of the loop, the loop. And when the people analyze, in this case, this event in different wavelengths from the X-rays to the radio, in the whole electromagnetic spectrum, they observe these quasi-periodicities in the emission. If you see, we have here 7 peaks. They are damped in a short period of the order of maybe 15 minutes. And the question is, exists only one mechanism responsible to produce this particular behavior in the whole spectrum, or there are several mechanisms that produce the quasi-periodicity in the different wavelengths? So the questions are if, for example, are MHD oscillation the direct causes of plasma emission modulation? Why we can do this question? Because as we know, in the plasma there in the solar corona, the perturbations produce waves, and these waves travel with some characteristic speeds. In this case, the sound speed and the Alben speed. And when we calculate the period of these waves, these periods are of the order of seconds or minutes. And as I mentioned before, the periodicity, this quasi-periodicity is of the order, could be of the second or of minutes. So maybe the system is responsible to produce these quasi-periodicities because we have plasma there. So maybe the MHD oscillation are the responsible to produce this modulation in the plasma emission. But what happens if a wave interacts with the reconnection region and this produces quasi-periodic magnetic reconnection? We don't know, and we are not able to distinguish from the observation. But the other question is that maybe the reconnection region itself is capable to produce the quasi-periodic energy releases spontaneously, and we don't know. So, for example, in order to modulate or to propose or to answer this question, in 2006, Akaryakov and collaborator, they proposed that MHD oscillation induce quasi-periodic magnetic reconnection by external waves. For example, if you have this external loop oscillated with a King wave, this produces these waves that interact with this null point. This null point produces quasi-periodicities that travel toward these magnetic field lines, and then here at chromospheric level, we obtain the quasi-periodicities in hard X-rays, microwaves, and optical. But there are some another model that show us that, for example, in this case, McLaughlin and collaborator with these MHD simulations, they emulate this X point, this region here, and we perturb it in this particular way. And when they measure here the current from this perturbation, we can see that the current, the current density has these quasi-periodicities, and this explains that the quasi-periodicity magnetic reconnection are spontaneously induced by a particular perturbation in this reconnection region. But the other answer could be that the MHD oscillation induced the modulation of the emission. For example, when we think in a coronal loop that is very short, because there in the active region they are very short and thick, a eigen mode of this kind of cylindrical structure oscillate in a particular with particular mode, In this case, sausage mode because it's symmetric along the loop. And this kind of special modes, the periods of this oscillation are of the order of minutes or seconds, depends of they are fast sausage mode or if they are slow sausage mode. In our case, we study this proposal, how the MHD oscillation induce the modulation of the emission. Here I show you some events, observational event where the people measure in microwave how, for example, this region is oscillating. And when they measure in these different wavelengths and analyze with the wavelength spectrum the oscillations here in 8 GHz, for example, they obtain periods of the order of 30 seconds. When they measure the longitude of these coronal loops of the order of 30 megameters, they propose that, okay, a fast sausage mode is occurring in this system of coronal loops. Also in 2003, Nakarakov and collaborators, they again measure in hard X-rays, but also in radio emission, the oscillation of this particular flaring loop. Again, they obtain this periodicity in the emission. They calculate the Fourier magnitude, and they infer the temperature and the density. They were able to measure the longitude and the width, sorry, of the loop. And again, with this kind of period of the order of dozens of seconds, they propose again that a sausage mode is occurring in order to obtain this modulation in the emission here. So inspired in these observations, we try to modulate this coronal loop that is very short and thick with this kind of model where we have a straight loop, because we are looking for this symmetric sausage mode. We think that we have this phi symmetry here. So we perform 2.5 dimensional simulations. And the foot points are line tied to the chromosphere. And when we put this system in disequilibrium, as you can see here, we obtain a sausage mode. But the idea of this work was try to see which kind of perturbation are able to produce these quasi-periodicities. And as you can see here, we have here a loop. In this region, we have this current sheet, so we have a reconnection region. And in this region here, it can produce this kind of perturbation in the loop at the top part of the loop. And when we analyze what happened in the evolution with the MHD simulations, we can see that this kind of perturbation produce shock waves that they are very collimated by the magnetic field lines in this direction. These shock waves reach the chromosphere and then return. And when we measure the density, for example, in this point, we can see here this signal that is very similar to the quasi-periodic pulsation. And if you see the time here, the periodicity is of the order of minutes. So the slow sausage mode are able to produce the modulation in emission. But also another kind of perturbation of the equilibrium could be that if a flare occurs at the bottom part of the loop in the foot point, and if this loop is very short, the time conduction is very fast, and the time radiation is larger compared with the period of this modulation. And if this happens, the whole loop is heated almost instantaneously. So in that sense, the whole loop is in disequilibrium with external media, and this produces that the whole loop is oscillating with a fast sausage mode. Now you can see how is the oscillation, and now the periodicity is of the order of seconds. So in this case, the whole loop is oscillating with a fast sausage mode. But then, in order, because if you see here, we are analyzing the density, but in order to try to compare with the microwave emission, we use, and using our MHD simulations, we use this FOMO tool. This code emulates the microwave emission due to the heliosynchrotron phenomena. And in order to try to, because the heliosynchrotron emission is due to the non-thermal electrons, and in my case, I'm not emulating the non-thermal electrons. I only emulated the thermal electron. So this code think or assume that the distribution of the non-thermal electrons is proportional to the distribution of the thermal electron. With this assumption, we were able to reproduce the microwave emission. Here we can see the intensity, and when we perform the wavelength spectrum, we obtain a period of the order of second in order to try to compare with the observation. But also in this work, we see, in this case, we obtain this intensity from this pixel here, this point, this brown point here. But what happens if now I think that this loop is in another star, and if my instrument is able to measure a loop there, but it's not possible. But the idea is that for this sausage mode, we were able to obtain a signal, significant signal, that a sausage mode is occurring in another star. And from the simulations, we see that it's possible because there are some observational events that, for example, study these people, Doyle and collaborator. They see this flare in another star, and if you see here, we have above the flux these quasi-periodicities. In this case, for this case, is of the order of minutes, but this is signal that in another star, maybe there are loops oscillating, in this case, with a slow sausage mode. So the idea from the simulations is try to see if we were able to see the same, but in another stars, not only in the sun. So this is the summary of our results about the QPPs. And that's all.
Thank you. Can you hear me?
Yes.
Okay. Something happened to my keyboard here. So thank you very much, Mariana. Very interesting work. So I will take an advantage as I am being the host here. And I would like to first ask you about if you can comment something about this failure of CMEs being launched. If you can comment something related to the mass and velocity of the CMEs, and also the spots configuration for this pseudo streamer formation.
Okay. About the mass, when I show this, I forgot to mention that in our case, when we emulate, we only emulate the magnetic structure. We don't emulate the prominence. So in that sense, I don't measure the mass of the flux of the CME because I'm not emulating the prominence. And the more important thing in the mass is the prominence because it's heavier, the prominence there. The velocity with flash code is quite slow because with flash code we are not emulating the solar wind. So the ejections is very slow, of the order of 200 kilometers per second, for example. I'm not able to produce a fast CMEs with flash code because we don't emulate the solar wind. And I don't know if this answer your question, but then I don't understand what do you mean with the spot of the pseudo streamer?
Because I don't remember if you, I don't know if you remember my the presentation I did in the talk I did in Friends of Friends meeting in Cordoba. And I use like spot configuration to extrapolate the magnetic field of solar type stars. And and some of them, as we measured some try to estimate the magnetic field of them, are quite strong. So I was wondering if maybe the sunspot configuration could maybe interfere in the pseudo streamers in your simulation. And because what I'm trying to say is that probably some of CMEs that we simulate for those stars, maybe they could be trapped by the magnetic field. So I was wondering that maybe the spots configuration could interfere on the pseudo streamers.
When you said a spot, you are talking about an active region.
Yeah, yeah.
Okay. Let me let me see. In my case, we don't emulate active regions because when we try to do it in flash code, and as you know, the strength of the magnetic field in that region are very strong, we have problem with the code. When you have to, when you try to increase the magnetic field, the code breaks. So in that sense, we don't emulate active regions, but the active regions, if I understood correctly, you have only open field lines there. So in that sense, I don't know how this can produce that the CME failed because, but I don't know. I don't know. But for example, now here in Graz with Astrid Veronique, we are trying to understand from the observations why the CME failed, and we are analyzing several failed events that occur near an active regions, but that I'm not interested to study because I'm not able to emulate it. But I think that maybe the failure is not due to an active region, because I think that you need this magnetic cage. So you need these closed field lines in order to prevent the ejection. But I'm not sure. I'm not very, very sure.
Oh, yeah, no problem. But thank you, because these just talking about pseudo streamers, I think this can like improve the discussion in my research. But thank you. And I see Gigi has a raised hand, so please, Gigi, go ahead.
Hi, Guillermo.
Hola Mari, ¿cómo estás?
Hola, todo bien.
First of all, I lost your explanation, your talk about CMEs because I was wrong. I thought that your talk started at 10:30. It was just losing time here, waiting 10:30, and then no, it's 10. So,
Oh,
but
no
anyway,
problem.
CMEs is not my subject, so I got exactly QPPs, which is most interesting for me.
Okay, super.
So, we have observations at very high frequencies compared with the microwave you've shown,
Mm-hmm.
that showing QPPs with quasi-periodicities below 1 second. Do you
Yes.
think that MHD can produce QPPs with less than 1 second quasi-periodicities?
Mm. If this depends of the Alben speed, and this is very fast, maybe yes, and the if the coronal loop is very short, or the width is correctly, maybe I think that because depends of the length, the speed, and the size of the loop. So I think that could be possible. Yes, yes.
Okay, could be interesting maybe to model something like that and compare
Mm-hmm.
with our observations.
Yes.
And also, this is something we talked in Cordoba when I
Mm-hmm.
was there about your gyrosynchrotron
Yeah.
models and the compute. Because it's in terms of quasi-periodicities is okay, but the intensity is orders of magnitude lower than those that we can detect with our instruments, 10 to the minus 5 SFU. But if I understood well, it is just 1 pixel that you compute, isn't it?
Yes.
It is like this?
Mm-hmm.
Yes. Okay. Yeah, you should integrate this along the volume. Probably you will get numbers more similar to this of the other
Okay.
power.
Yes. But that is my problem, that I'm not observational people, and for me maybe this number, I'm sure
Yeah.
is wrong. So yes, I need help with that.
Well, if you
In
just
order to
take
compare.
volume, the general volume, and integrate,
Yes.
probably because
Mm.
the volume should be very big. How big is the pixel? Well, half. I see.
But in this
Half,
case, okay, there I show you this slide in 2.5, but when I do these calculations, I do a revolution in order to obtain a cylinder, and
yeah.
then the code, this FOMO code, integrate along the line of sight. So in that sense, I think that we are taking into account the volume, but I'm not sure if the intensity is very low. Okay, I have to
Yeah.
compare better.
Yeah. Yeah, well, this is unobservable. 10 to the
Okay.
minus 5 is, I think maybe Alma can observe something like this, 10 to the minus 5. But it seems maybe, well, the hypothesis that the number of non-thermal electrons goes with the density of the thermal electrons. I don't know, but something
Yes.
like that.
No, but maybe that is a problem, because with this code, you assume, or you can assume a double low spectrum, or a single one, or in this case, if I remember, the non-thermal electron is 4,000 smaller than the distribution of the thermal electron. So maybe if I change this number, this intensity will be or will
Well,
I don't know.
gyrosynchrotron is linear with the number of electrons. So you can
Okay.
see how much electrons you need. Just
Super.
multiply.
Okay. Super.
Okay, I think Paulo has something to say now.
Yes. Thank
Thank
you,
you,
Guillermo.
Mariana.
Thanks. Thank you, Mariana, for the talk. I have curiosities about the CME part, but I'll leave that to another part, another thing, because the QPP thing is more, let's say, interesting to me here in this discussion. One thing is, I'm thinking I should read this paper. I wasn't aware of your paper there. But just comment, I agree with Gigi here. It might be interesting just to check a integrated emission, because yeah, there's a whole thing on the observations and how people do the filtering, like Kashapov did there, depending on how you filter, like you can, your QPP signal might be stronger or weaker depending on how you filter things.
Yes.
But I'm wondering here, because I did some QPPs in the past, 10 years ago already. Geez, time flies. And mostly soft X-rays, right? Using ghost data, and then compared with some hard X-ray as well. So, and we had a whole discussion. I remember reading lots of Nakayakov's papers at the time, right? The whole ideas on the kink modes and sausage modes and all that. And I'm thinking here if you could comment on in terms of the modeling you're doing, and right, especially in the case of the observation you showed, right? Because usually when people discuss the QPP frequency period modes, the discussion goes into one single loop, right? Because you need one loop to give a length scale. But when you look at the actual flares, there's a whole but a distribution of spatial scales, let's say, right? Loops of different size. And we had somewhat of a discussion this. I remember Nakayakov didn't like my our discussions back then in our papers. Yeah, your paper is nice. I don't agree with your conclusions. Because it goes into this discussion, right? How can you the theory or the models go into single loop discussions, but then observations show a different distribution of scales. What do you have in mind in terms of this matching or trying to conciliate those things in these scales? I hope it was clear.
Because first, all the time when I try to compare with observations, I realize that I don't know anything about observation. And because, for example, a lot of time I try to ask to Guille, because I'm not sure what you are seeing, because you are seeing the loop, or is the whole loop?
It's the whole thing, yeah.
So for me that is very confused. I'm emulating only one loop, but it's thick, but maybe, but also there is another discussion about which are the components of this monolithic tube. Is only one tube, or you have a very thread, a huge amount of threads inside?
Smaller, yeah.
So, but for the modeling, we know that it is very complex. Try to reproduce the whole dynamics, because it's complex because the equations, because in my case only I am using ideal MHD equation, so I don't have terms or resistivity. Then you have, I do a lot of assumption about the symmetry. Only I have a saucer mode because I need to do this simulation in 2.5 dimensions. And then you have to be able to reproduce the synthetic emission from your simulation in order to compare with observation. It's not easy task to do. But yes, I see that, okay, in the community, we try to do this, to this bridge between the observation and modeling, but okay, I'm not very sure how to
how those two parts are close, getting closer
Yes.
together, let's say, right?
Yes, but from these very simple simulations, okay, we try to understand maybe only a little part, and in order to contribute, but
Yeah, of course.
very
Yeah.
difficult. Yes.
No, makes sense. Yes, yes. Like I said, it's a complicated thing, right? It's how to match those things. I remember again discussions with the QPP folks back many years ago when no conclusions are we got no conclusions for that. It's just maybe. So yeah, I'll be happy to continue this conversation via email at some point, because it's something that I dropped back in the day because it was too much. But it's the whole thing. It's not just like you have the sausage mode, but that should modulate the trapping precipitation of electrons. That should also modulate the characteristic emission. That should modulate the hard X-ray emission.
Yes.
It's a lot. But anyway, so yeah, thank you. I understand there's a whole problem.
Yes.
To match those. Yeah.
Thanks
Thank
for
you.
your
Thank
comment.
you. Yeah.
Adriana, go ahead.
Hi, Adriana.
Hi, hello. Hi, Mariana. Thank you so much for a very interesting talk and very interesting results. I mean, I don't know if it is a question. I don't know if there is an answer to it, but I'll go ahead and ask it anyway. Right now, I'm trying to connect, see how our observations at millimeter wavelength, at 45 and 90 gigahertz from the Poemas telescope in Argentina correlate with CME launch. And from the 50 flares that I'm studying, we have 29, which is almost like 60% of the flares have either a halo or partial halo CME. I haven't really looked. I'm going to go back and look, like just regular CMEs without being halo. But my question is, would you say that with every flare, you would have a CME, a potential CME? But in some cases, the reason we don't see the other, let's say 40% or less than that, is because they're quenched by the strong magnetic field. My question is, do you think like flares and CME, they would always occur, but then the CME is held, you use the term, I forget now, it's not, it failed.
Okay, so from that point of view, we know that there is a relation between the CME and flare of the order of 80%. Every flare, not every, 0.8, yeah. Okay, I don't know how to say, sorry.
For every 10 flares, 8.
Sorry. But if this is if the flare is related with the failure of the CME, I don't think about that.
Yeah, my question is, are these 20% cases, failed CMEs? Like the magnetic field above it weren't strong, then we would have like 100% correlation.
Okay.
Or it's just going a little bit too far.
No, I'm sorry, I didn't think about that, but I don't know. I'm not sure if could be a relation, but now I will think about that. Now I will think. Yes.
Yeah, because the good thing with the microwave observation is that I combine it with microwaves from RSTN, so I can do a gyrosynchrotron fitting, and I can get estimates of the magnetic fields. So it would be interesting then, like to try it more. That's an idea that occurred to me. while I was listening to your talk. Well, like maybe if I can get the magnetic field, like, and look at, well, flares or microwave sources with this, which I produced with the, like within this magnetic fields, how they correlate with CMEs and how they do not, the ones that have and the ones that do not have a simultaneous CME.
But do you have work about that?
Oh no, that's just an idea that occurred to me.
Okay, because if not,
I have like maybe about 15 flares, maybe 20, which I already have the gyro synchrotron model, for which I already have the magnetic field, but I haven't done that for the ones that do not have CMEs. I'm only looking at the ones with the CMEs. But I'll let you know, and I'll bring you into this discussion when I have the result.
Thank you, Adriana. Thank you very much.
Thank you.
Does anyone else would like to make a question or maybe a comment? Don't be shy, people. All right, then. If no one else has a comment or a question, I would like to thank Mariana again for presenting this very nice work. Also thank everyone here that is watching this presentation with us. And that's it. We see each other. I think the next we didn't set, right, Eduardo, the date for the next seminar, but I think it would be with Mariana's indication.
It will be in 2 weeks ahead, yes.
Oh, okay.
Yeah.
She's very happy, Paula?
Paula.
Yes.
Yeah.
Oh, yes, because she's here in Graz, and when she showed me her work, he mentioned the work of Paulo, and I think that, yes, and I think that it will be very helpful for her that you Paulo, see her work, and maybe because she's doing the master from Colombia, and she's trying to do some statistical study about if she is able to predict a flare, and she's trying to measure some previous signal from the flare in order to see if she's able to predict it. So, and she showed me your work, and I said, okay, you have to present your work there in Mackenzie seminar.
It's very interesting. Also, Mariana, Fabian, if I may, so just Mariana, please do send me regards to Astrid and Manuela.
Okay.
Sincere regards. It's been a while. We exchanged a few emails a few months ago, but yeah, but I had a undergrad student that stayed with them for a few months.
Okay.
Because coincidences. So yeah, but please send my regards to them.
Okay, thank you.
Thank you.
I will do it.
And just one last thing, Mariana, if you can share the papers with me, please.
Yes, I will do it.
Yes, please.
And then I can forward for those that are interested.
Super.
We can share in our group to all the students. That'll be interesting. Yeah, both the CME stuff and the QPP stuff.
Okay.
Yeah.
Super. Yes.
Thank you.
All right. See you, people. Thank you. Bye bye.
Bye.
Thank you again, Mariana. Thank you. Bye.
Bye. Thank you.
Thanks, fun.
Bye. Thank you.
Bye.